the calculation of the partial transfer function from the applied voltage to the motor speed must have looked rather complicated. Of course, one of the reasons for taking it up was to remind you about signal flow graphs and use of the gain formula for making some calculations of transfer functions or transmittances using the signal flow graph. We will do it in a different way now, using the earlier concept of a block diagram, and in this case the block diagram is also going to be fairly simple. In fact, the block diagram is more meaningful than the signal flow graph, but remember that if we look at the block diagram, we can apply a rule similar to Mason's gain formula to the block diagram as well. Let us see how we can do that. What we will do is, now again our starting point is the two equations. That is all we know about the motor and the drive, but we will draw the block diagram so as to represent those two equations in a particular sequence. So first look at the voltage equation. We have the applied voltage EA on one side, and we have the back EMF and the armature current multiplied by the operator SLA plus RA. Remember, now we are looking at the transient or the non-steady state behavior, therefore we have the derivative term, and therefore we have the armature inductance term, and we are taking Laplace transforms of all the variables involved, both the current, the speed and the voltage as well as the load torque, all of them. We are looking at only Laplace transform, or sometimes one says that we are looking at the problem in the transform domain or in the so called S domain, whereas in contrast the differential equation is said to be in the time domain or T domain. And the Laplace transformation method allows us to go from T domain to S domain and then back to T domain. So we are now in the S domain or in the Laplace transform domain. So from that equation I can write EA as a signal which is coming in to a difference device. This is not a physical difference device, this is only a conceptual difference device. So it takes the difference of EA and the back EMF term, which is KB omega. So I will write that omega out here as the output signal transform, and I will show a gain factor or a block here, KB. So we have EA minus KB into omega. This is the output of this difference device, but that equals RAIA plus LADIA dt in the time domain, and therefore SLA plus RA in the S domain. And therefore in order to get the transform of the current IA, capital IA, I will have to put into this block 1 divided by SLA plus RA. This also looks like a transfer function, but remember that this EA minus KB omega is not an actual physical signal, as I have told you earlier. It is not that the back EMF appears as a separate voltage which gets subtracted from the applied voltage. The motor action is described through a back EMF. So this 1 by SLA plus RA sitting there is not really a transfer function of a system or a device as such, but it represents the relationship between the armature current and this difference EA minus KB into omega. So I have written there 1 over SLA plus RA. So there is a block there. Now this IA produces a torque, and therefore I have that proportionality constant KT, the torque constant. So this produces the motor torque. From this motor torque, and I will put another difference device, the load torque gets subtracted. So I am showing TL as an input to this difference device with a minus sign. So KTIA is the motor torque, subtract from that the load torque, and that is the torque that is available for accelerating the motor as well as for overcoming the viscous friction. And therefore this will be multiplied by what? If you look at the torque equation, we have KTIA equal to TL plus two terms, one corresponding to friction, the other corresponding to the moment of inertia. And therefore in this block I will have 1 over Sj plus Kf. So this will be the block diagram for the system. This looks simpler than the signal flow graph, doesn't it? The signal flow graph had two input nodes, two output nodes, and there were transmittances from one of them to the other, and it looked a little messier. Also, instead of writing transmittances along the lines in the signal flow graph, if I show blocks like this, it stands out a little better. Remember that these are not actual physical devices. This KB is not a physical block. The motor action is such that there is a back EMF, and the motor action is such that the difference between the applied voltage and the back EMF is what determines the current. Similarly, the motor torque is not produced in a separate place. The motor torque is produced at the same time there is the load torque opposing the motor torque plus the friction, and the difference is available for accelerating or decelerating the motor. So none of these blocks really stand for any separate physical device as such, except perhaps the moment of inertia and coefficient of friction Kf part. This could stand for the drive part of the whole system, that is the load and the friction and the moment of inertia of all the masses on the shaft. Now from this block diagram we can write down the transfer function, and remember what I told you right in the beginning today, that we can think of this in a way similar to signal flow graph. There are arrows here, one can look at and see a loop here, one can talk about forward paths and so on, and so one can deal with this block diagram very much like a signal flow graph, and we can therefore use the Mason gain formula for the block diagram as well. And so if I do that, then what will I get? I will get the output signal omega, or the Laplace transform, equal to a transmittance from EA plus a transmittance from the load torque, because there are two incoming arrows, EA is one, TL is another. So I will have omega as a sum of two terms, one of them is a transmittance multiplying EA, and this I have called the partial transfer function from EA to omega, that is, it gives you the effect of EA on omega, and the other is the partial transfer function from load torque to the speed. Remember, all of this is only a part of the response. We have ignored, or we have kept outside, the part corresponding to the initial conditions, the armature current at time 0, t equal to 0, and the motor speed at time equal to 0. We have left out that part, we are only looking at a part of the response. Moreover, the initial conditions of the input, of course in this case the inputs are EA and TL, EA also could have an initial condition, that also is being kept outside of this calculation or this block diagram. Now what will be the partial transfer function? Once again we can look at the loop, and one can look at the loop gain, and the loop gain will turn out to be exactly what it was earlier. So looking at the loop, then we have one transfer function 1 over SLA plus RA, that gets multiplied by KT, then there is also 1 over Sj plus Kf, and as we go through the difference devices we have to take care of the sign. So far it's okay, 1 over SLA plus RA into KT into 1 over Sj plus Kf, because the signal from KT, output signal from KT goes through with a plus sign, so no change of sign. Then this is multiplied by KB, we come back to our starting point, but then we go through a minus sign. So this multiplied by -1 or with a negative sign is the loop gain, and this is precisely our delta in the signal flow graph gain formula. And you can check that we have got the same thing as earlier. So we have KT KB divided by these two linear factors in the denominator, SLA plus RA and Sj plus Kf, and we can write them using time constants as we had done earlier. So that is delta. And now for the gains or the transmittances from EA to omega, there is only one forward path, and the gain of the forward path again is very easy to see. Simply go through those three transfer functions, 1 over SLA plus RA followed by KT followed by 1 over Sj plus Kf. Now that is the gain of the forward path. That is going to be multiplied by only 1, because delta was 1 minus that, not minus that. This is a mistake that students make, and I also made just now. It is 1 minus minus, therefore 1 plus this thing. This thing with a minus sign was the loop gain, and the delta was 1 minus sum of loop gains plus sum of products of two non-touching loop gains, etc., etc. So this is delta, 1 plus that, remember, not just minus. So this is the denominator, and the numerator is simply the forward path transfer function. Similarly, the forward path from TL to omega, now here we have to take care of the minus sign because TL enters the difference device with a minus sign. So minus 1 into the next transfer function block 1 over Sj plus Kf, that is all in the forward path from TL to omega. So that multiplied by 1 once again divided by delta is the transfer function from the load torque to the applied voltage EA. The block diagram is a little less cluttered than the signal flow graph, but the way we look at the block diagram and compute the transfer functions is exactly like we did for the signal flow graph. There is not any difference, and I told you earlier that the signal flow graph concept evolved out of the block diagram concept. In some situations the signal flow graph is easier to deal with, in some other situations, especially when you want to get some insight into what is going on, the block diagram is the convenient thing to deal with. So this is therefore what we have right now. Now, as we saw earlier, the disadvantage of this kind of a drive is that it can be made to run at the desired speed for nominal or rated conditions. That is, given the rated load torque, in other words the load torque at which or when for which you want the motor to run at a specified speed, say omega 0, one can make calculations and decide what the value of EA, or in our case earlier capital EA, now small ea, should be. In other words, knowing the load torque which is to be overcome, knowing the speed at which the drive is to run, one can calculate the voltage to be applied, and then we expect that the drive will run in the steady state at the desired speed. But should TL change now, then the drive will not run at the desired speed. And by what amount will the speed change? Now this is something we can find out. We can look at the partial transfer function from omega to TL. So let me write it here as omega by TL, but remember that this is only a partial transfer function. So this will be equal to what? Delta that we had as before in the denominator, multiplied by, in the numerator we have minus 1 over Sj plus Kf, and that is all. So this is the expression for the partial transfer function from omega to TL. And now what is the effect of a change in TL? That is what we want to compute. We will look at the change in TL, the effect in the transient state, that is, as the load torque is changed, let us say suddenly from one value to another, what will happen. But if we want to find out the effect in the steady state, then this is something we had done earlier with the signal flow graph. We can do the same thing here because we have the same transfer function, that is, use the final value theorem of the Laplace transform theory and get the value of the speed as t tends to infinity, and therefore we can look at the change in torque and find out the corresponding change in the steady state speed, and the minus sign here shows that if the load torque is increased, the speed will decrease. So the drive will not run at the same speed omega 0 when the load torque is changed. So this was one of the defects of the drive that we wanted to overcome, and we thought that we could do it by using feedback, and to that we will be coming very shortly. But what if I want to find out what happens in the transient period, that is, when the load torque is changed suddenly from some value to some other value very quickly, what happens to the speed? We know that the speed will change and eventually it will come to some new constant value, that is new steady state, but we want to know what will happen in between, and the transfer function will enable us to solve that problem. And the qualitative study of the transfer function by means of the pole zero diagram will also enable us to say something about what will happen in the transient period. So that is something we will take a look at now. So for that, let me rewrite the transfer function now. So omega divided by TL equal to, now clearing the denominator, that getting rid of the Sj plus Kf from the numerator as well as the other factor from the denominator, we will have this is equal to minus SLA plus RA divided by, we will have SLA plus RA into Sj plus Kf plus Kt Kb. The transfer function from the applied voltage to the motor speed was different, the numerator was different, Now in the numerator I have a factor SLA plus RA. In the transfer function from the applied voltage to the speed, there was no factor involving S in the numerator. All we had was a constant. There is a difference now. We have a factor SLA plus RA with a minus sign in the numerator. What does that mean now? This means that this transfer function or this partial transfer function has a denominator. The denominator is a quadratic, and therefore I can imagine the quadratic factorized into its two factors, and this quadratic is exactly what we had earlier for the other transfer function, because it is the common delta. It comes from the common delta. So the denominator is a quadratic, which means there are two poles. This transfer function has two poles, but it has something in the numerator which is not a constant, but it's a linear or a first degree polynomial, and therefore it has a 0. So the situation is different now. For this transfer function has two poles, but it has also one 0, and the 0 is given by what? SLA plus RA. I told you it can be rewritten by pulling out LA as S plus 1 by tau armature, and so the 0 is at minus 1 by tau armature. If tau armature is the time constant, then minus 1 by A is the location of the 0. Tau A is of course positive, so minus 1 by tau A is real and negative, and therefore the 0 is in the left half plane. Not only that, it is on the real axis, what is called the negative real axis, and the 0 I told you earlier is indicated by putting a circle like this, and so I will put the circle here and write down minus 1 by tau A. So this is the location of the 0. What about the locations of the two poles? Well, I told you last time we looked at this situation that depending on the various values KT, KB, etc., we can have a number of different situations. We can have two distinct real poles, we can have two coincident real poles, and we can have two complex and conjugate poles, but all of them lying in the left half plane. And so different situations are possible. As far as the 0 is concerned, the 0 is what I have put down here, but the poles could be one of those alternative locations. There could be a pair of poles on the negative real axis, there could be, that is, distinct poles, there could be a repeated pole, that is a second order pole or a second order factor corresponding to a second order factor on the negative real axis, or there could be poles out in the complex plane, but all in the left half plane. Now what will be the effect on the response? Now for that, to find out the actual expression for the change, of course one has to get all the numbers, substitute the numbers, then find out the roots, and then go further. But right now I am only talking about qualitative understanding. So let's assume that the denominator polynomial is such that it has two real linear factors. Therefore the transfer function omega divided by TL will look like minus SLA plus RA divided by, and I have to pull out the factor LA and SJ out, and I get a quadratic S squared plus AS plus B is what I wrote last time, and therefore I will rewrite this finally as minus, and that SLA LA can also be cancelled, so I will get minus 1 by J into S plus 1 by tau A divided by, I will write this as S minus P1 into S minus P2 if there are two real poles, both of them negative, P1 and P2. If this is what is the case, that is, the numerical values of the parameters are such that the quadratic has two real factors like this with both the roots P1 and P2 negative and real, then this is what we have. Well, now I want to find out what will be the change in speed when I change the torque suddenly by a certain amount. Now a sudden change in torque can be represented by means of a constant function. Of course it is called a step function because we think of it as being 0 before t less than 0, and we think of the thing suddenly becoming non-zero at and following t equal to 0, and that's why it is called a step function. So now instead of considering TL, I am only going to consider the change in TL. So I will write down in this sense then delta omega divided by delta TL. Remember, this is not a ratio of two numbers, it is the Laplace transform for the change in speed divided by the Laplace transform for the change in load torque. This is the expression that I am writing, and that expression will be exactly the same transfer function that I have. But now I can think of applying the partial fraction expansion idea to the transfer function. Not only that, my delta TL will be what? my TL as a function of time is a step function. So the Laplace transform of that is 1 by s multiplied by the value of the step, or the amount of the step function, amount of the jump. So let's call that amount by, again there is going to be a conflict of notation, as I told you, small t for time and capital T for torque or transform. So this confusion is a little unavoidable unless we introduce some more symbols. Maybe I'll avoid the confusion right now by saying that, okay, let the change in torque in Newton meters be equal to what? Say alpha. Alpha is the change in torque. Say the load torque changes suddenly by amount alpha Newton meters. Alpha may be positive, the load torque is suddenly increased. Alpha may be negative, the load torque is suddenly decreased. And we are looking only at this particular kind of change when the load torque change is sudden, instantaneous, and therefore it can be represented by a step function. In that case, delta TLS, the Laplace transform of the change, will be simply alpha divided by s, and therefore the change in speed, the Laplace transform, remember, will be given by alpha divided by s into this transfer function. Now that will be what? That will be two factors in the denominator, s minus p1 into s minus p2, and something in the numerator. Now this you will recognize is a proper rational function. It's a ratio of two polynomials, and the degree of the numerator is less than the degree of the denominator. The degree of the denominator is 3, the degree of the numerator is only 1. Such a rational function is known as a proper rational function or a proper rational fraction. Now as soon as we see that, we can apply the partial fraction expansion idea to this, and therefore what will we have? We will have a partial fraction expansion which will have 3 terms. There is one factor s, so there will be one s in the denominator, plus there is another factor s minus p1, so there will be s minus p1 in the denominator, plus there is a third factor s minus p2, so there will be a third term s minus p2 in the denominator. So this ratio of the two polynomials can be written as a sum of 3 proper partial fractions. Each one of them has only a first degree polynomial in the denominator, s, s minus p1, s minus p2. In the numerator, I will have some constants a1, a2, a3. So delta omega s is given by a1 by s plus a2 by s minus p1 plus a3 by s minus p2, where p1 and p2 are negative. So for example, p1 may be minus 2, p2 may be minus 3, so the denominator factors look like s plus 2, s plus 3. Fine then. What can we say about the inverse Laplace transform, or what can we say about the change in speed? The change in speed delta omega t with a small letter omega and function of time will therefore be what? Corresponding to a1 by s, we will have just the constant a1. Corresponding to a2 divided by s minus p2, p1, we will have a2 into e raised to p1t plus a3 e raised to p2t. So as a function of time, it will consist of 3 terms, a number or a constant a1 and 2 other terms which are changing with t. But remember, p1 and p2 are negative, so these 2 terms are decaying exponentials, and therefore after enough time has elapsed, now each one of them corresponds to a time constant, we can take the larger of the 2 time constants, and if we wait for say 5 times that or 10 times that duration, then both of these would have become nearly 0, and what would remain is a1. Now this a1, using the partial fraction expansion approach, can be calculated fairly easily, and as a result one can find out the change in speed rather quickly. To find out this a1, go back to the partial fraction, the transfer function. So let me rewrite the transfer function once again as delta omega divided by delta TL equal to, now I am going to use the letter g once again, but this g is different from what I may have written earlier. As I told you that the preferred letter for a transfer function in control theory literature is capital G and capital H if it's something that has to do with feedback or in the feedback path. So I'll write here g of s. This g of s is of course an expression that we had written earlier. So I have delta omega divided by delta TL equal to g of s. Delta TL once again was simply alpha by s, so delta omega by s was equal to alpha gs divided by s. Remember, the gs is a ratio, it's not simply a polynomial, it is a ratio of two polynomials. In fact, that is why we had two factors in the denominator and we had one factor in the numerator. Now, this a1, the coefficient that goes with that partial fraction expansion term 1 by s, can be obtained by this following simple device. Now, this is something which is proved in your algebra textbooks which deal with partial fraction expansion. So, look up a good algebra textbook that discusses partial fraction expansion. But the way to obtain that a1 is very simple. All that you do is you look at this expression, suppress the factor s and then put s equal to 0. Suppress the factor s, because if I do not suppress it and if I put s equal to 0, then I will have a 0 in the denominator, which indicates some trouble. No, but the rule says that suppress the corresponding factor, in this case s, from the denominator and put s equal to 0, that is the root to which it corresponds. The term s would correspond to the root 0 because it will be 0 at s equal to 0. So, put s equal to 0, that will be a1. Therefore, immediately we have a1 equal to alpha g0. And so, we have an expression for the change in speed in the steady state when the load torque is changed suddenly and kept constant thereafter. The amount by which the load torque was changed was alpha, and we have g0, the transfer function from the load torque to the speed evaluated at s equal to 0. That is, in the transfer function simply replace s by 0 and whatever number you get, that number is g0. It will turn out, as you can check for yourself, that this g0 is not 0, in fact it is positive. No, it is not positive, it is negative. Why? Because if alpha, the change in load torque, is positive, if the load torque increases, I expect the motor speed to decrease. So, just check that this is negative because there was a minus sign sticking out in front. So, g0 is not 0, it is negative. So, an increase in load torque results in a decrease in speed, a decrease in load torque results in an increase in speed. And so, for a instantaneous or sudden change in load torque, we can find out the change in speed as a result of that change in the long run, that is in the new steady state. I am assuming that the motor was running at some constant speed with a constant torque. Suddenly the load changed its nature, say the job was changed or some friction, additional friction was encountered on the job or whatever. As a result, the load torque suddenly increased. The motor speed will then reach a new steady state value. But that is not all that we can get from this. The two terms which go to 0 tell you how the speed changes, because if I write down the expression for delta omega t, then it has a1, this is the final value of the change, but in between, that is before that final value is reached, you have these two exponentially decaying terms. Now, of course, e raised to p1t, e raised to p2t are exponentially decaying. Why? Because p1 and p2 are negative, the poles are in the left half plane. Therefore, correspondingly we have exponentially decaying functions. But their multipliers a2 and a3 may not be both positive. So, one of them could represent an exponential decay, but which is with a positive sign. The other could represent an exponential decay with a negative sign. One has to look at the actual numbers and work out what a2 and a3 are going to be. That thing is getting added to the change that will survive as t tends to infinity, namely the change in the steady state. And one can say now that how long will the motor take to reach the new speed? You have the two poles p1 and p2. Correspondingly, you have the two time constants. The time constants are reciprocals of the absolute value of the poles. The poles are negative. Therefore, I have to take their absolute value and take their reciprocal. That is the time constant. So, one of the time constants is 1 by absolute value of p1. The other time constant is 1 by absolute value of p2. And therefore, whichever is the larger of the two, say 5 times that or 10 times that, is the time by which the motor would almost reach its new steady state value. And so, by drawing the block diagram and by using the Laplace transformation, by working out the various transfer functions or the expressions that we have associated with the blocks, and by applying the gain formula for the block diagram as we did earlier for the signal flow graph, for a special change in input, namely the step change in input, we can calculate the change in speed as a function of time exactly. From that we can also find out change in the final value, but we can also find out how fast the change will take place or how long it will take for the speed to go to its new value. That requires knowledge of the two poles or the corresponding two time constants. Now this was for the case when the quadratic had two distinct linear factors, or the partial transfer function had two distinct poles in the left half plane lying on the real axis. Now we have to consider the other two cases. Remember, we are only doing some kind of a qualitative study. I am not actually calculating anything here, but I am trying to figure out beforehand what could happen. So let us consider the second case. The denominator factor is repeated. As a result, now what I will have is delta omega s will be something in the numerator, that polynomial, first degree polynomial will remain, divided by, for a step change in load torque, s will be there once again, but multiplied by, say, s minus p1 squared, because there are two factors which are the same. So instead of s minus p1 into s minus p2, I have s minus p1 squared. This will be the expression for the change in speed, the Laplace transform of it, when there is a step change in the load torque, and the step is of the value alpha, as we had talked about. So I will put that alpha in front here. So it will be alpha multiplying some expression divided by s into s minus p1 squared. Now the same thing once again, apply partial fraction expansion to this. Unfortunately, the partial fraction expansion is not as simple as it was earlier. However, one of the terms is exactly as before. One of the terms is simply a1 divided by s, corresponding to the factor s in the denominator. But because I have the factor s minus p1 square in the denominator, I have now two partial fractions. One of them will have s minus p1 as the denominator, and the other will have s minus p1 squared as the denominator. The numerators will be a2 and a3, again some constants which have to be determined. The partial fraction expansion result or theorem tells you that this expression can be rewritten like this. To calculate a1, a2, a3, you have to do some work. You have to know what all the numbers involved are and do some computations. But qualitatively, we know that this can be rewritten like this, and therefore we know that delta omega t will consist of three terms. And what will they be? Corresponding to a1 by s, I will just have the constant a1. Corresponding to a2 divided by s minus p1, what will we have? a2 into e raised to p1t. And remember, p1 again is negative, so this is the exponentially decaying term. So there is no difference. But the third term has s minus p1 square in the denominator. Because of that, the Laplace inverse of that has to be used, and the Laplace inverse is a little different. So it is a3 multiplied by e raised to p1t, but that is not all, multiplied also by t. So there is this additional factor t that has sneaked in here. It is exponential but multiplied by t. And I told you earlier, to plot such a function, product of the exponentially decaying function, that is the exponential which decays, multiplied by t, and see that this thing does not decay like the exponential does, but it starts off from 0, builds up to a value, and then goes to 0. The graph of that t e raised to p1t for a negative p1, because at t equal to 0 it is 0, starts off here. In the long run it goes to 0, the exponential negative exponent dominates the growth of t, so it goes to 0, but in between it reaches some kind of a maximum value, and so this is the graph of t e raised to p1t. However, as far as the steady state is concerned, there is nothing to worry, because e raised to p1t is going to 0 as t tends to infinity. Even this factor or this term t into e raised to p1t goes to 0 as t tends to infinity. Now luckily you can verify how long it takes for a term like this to become sufficiently small. If it was only the exponential, I would talk about 5 time constants or 10 time constants. You can find out for a product like this, when does this become sufficiently small. This will be homework for you. By sufficiently small, of course, we may say it becomes, say, 10 raised to minus 3, 1 by 1000, if that is sufficiently small, or 1 over 10 raised to 4, 1 by 10,000, if that is sufficiently small, that is 0.1% or 0.01%, depending on what you mean by sufficiently small. Find out the time t by which t e raised to p1t becomes 10 raised to minus 3. So let me write this down. Find time t such that t e raised to p1t for a given p1 negative becomes 10 raised to minus 3, or becomes 10 raised to minus 4, or becomes 10 raised to minus 5. How many time constants should elapse before you can say that the function has become now 1 by 1000, therefore it's negligible, or 1 by 10,000, therefore it's negligible, and so on. So from this transfer function manipulation, we can say once again that in the steady state there will be a change that will be given by a1 as before, and this a1 will be obtained by exactly the same technique that I indicated to you earlier. Suppress the factor s and then look at, put s equal to 0, you will get what you have. So it will be again alpha into g0, where gs is the transfer function from the load torque to the angular speed. So there will be a steady state change in speed, and in the transient period the behavior will be governed by the time constant corresponding to the exponential e raised to p1t, but also this additional exponential multiplied by t, which can make a little difference to the time constant computations. If instead of a sudden change in load torque we think of a more gradual change in load torque, then we have to find out the Laplace transform of that change and then work it out in detail, find out what is the Laplace transform of the speed change, take the Laplace inverse, and get thus an exact expression for the change in speed as a function of time. Usually one works with step changes. In some cases one thinks of what is called a ramp input, that is changes which correspond to a ramp. In this case, of course, it's unlikely, because the load torque, I can very well conceive, can change suddenly from some value to some other value, but I cannot think of a situation when the load torque will just go on increasing without any limit. And if that does happen, then of course I expect that my motor will finally come to a standstill. The motor will simply not run because it will not produce enough torque. In fact, there is an upper limit on the amount of torque that the motor can produce. Before we look at the third case, that is when the poles are in the complex plane, let me draw some waveforms or graphs of the behavior of the speed as a function of time. So here is omega and here is the time axis t. I am plotting omega t versus t. Let me assume that before t equal to 0 the motor was running at some constant speed, so I am showing it here on the left hand side of the t equal to 0 line, and then I make a sudden change in the load torque. If the load torque was increased, then by what I have just now discussed, there will be a new steady state speed which will be less than the older one, and therefore I am showing it as this dashed line, and of course for the sake of clarity I am showing the speed change as being very significant, and that could very well happen. The load torque may get doubled for all you know. So the speed starts off here at t equal to 0, there is a sudden change, the speed is ultimately going to end up at this steady state value, and in between it is going to make a transition, that is the transient. And in the first case, when we have the exponentials, most probably the transition will be like this, that is the speed will start decreasing and go on decreasing till after 5 or 10 times the larger of the two time constants, the speed would have virtually become constant at the new and lower value. On the other hand, if the load torque was decreased, then the speed would start increasing and keep on increasing till after a certain time equal to say 10 times the larger of the two time constants, the speed would have become almost constant at the new higher value. So with increase in load torque the speed drops, with decrease in load torque the speed increases. And this is precisely the problem with our drive, that is the drive speed, if we are not making any adjustment of the applied voltage, cannot remain constant as the load torque changes. Remember, this was not the only reason for thinking of feedback. Load torque, thinking of it as a disturbance, something which is not under our control, That was one thing. And what was the other? The other was lack of certainty about the parameter values, or the parameter values also changing over a period of time and so on. But we are not looking at those effects right now. We are only going to look at the effect of a disturbance like signal such as the load torque. Okay. In the second case, when the roots coincide, so when the two poles coincide, or there is a second order pole or a repeated root of second order or multiplicity 2, these are all alternate ways in which people talk about it. Multiplicity, order of the pole, repeated roots, one should be familiar with these various terms. In that case again, there will be a change from the initial constant value to a new constant value, but the change may not look as simple as I have shown here because of that t term. The t term can make a slight difference, and after you have plotted t e raised to p1t, you will realize the difference. Okay, so this is what the speed versus time curve will look like when the load is changed suddenly from one value to another. Load torque is changed suddenly from one value to another. Now we are ready to look at the third case. Now what happens in the third case? In the third case, then I will have delta omega s once again equal to alpha divided by s, that is the Laplace transform of the change in the load torque as before, multiplied by, once again there is a polynomial in the numerator of degree 1, and in the denominator now I have a quadratic. So let me write it once again as s squared plus as plus b, whose roots are not real but are complex. Now one could, as before, factorize this into s minus p1 into s minus p2, carry out the partial fraction expansion, apply the Laplace inverse. The only trouble, so to speak, will be that this p1 and p2 are going to be complex, and therefore the numerators in those partial fractions will also be complex numbers. So one will have to do some complex arithmetic. Of course, I suppose you are already familiar with complex arithmetic and how to do it using your calculator. But we can avoid the complex calculations. In fact, we are not going to do any calculations at all. As I told you, I just want to get some understanding of what is likely to happen. So we can avoid that entire thing as follows. Now this requires that the quadratic s squared plus as plus b be rewritten as follows. What we do is we take the first two terms, s squared plus as, and do what is called completing the squares. So I will write that as s squared plus as plus a square by 4, but then I have added this a square by 4, so I will subtract from that from b, so b minus a square by 4. So I will have s squared plus as plus b, the quadratic, written as s squared plus as a square by 4 plus b minus a square by 4. Now this first polynomial is simply s plus a by 2 whole squared plus b minus a square by 4. Now what is the discriminant of this quadratic? Discriminant of the quadratic delta is a square minus 4b. Now the case of complex roots is when this discriminant is less than 0, or when a square is less than 4b, or when b is greater than a square by 4. So this term b minus a square by 4 is positive. Because it is positive, we will rewrite it as the square of some number, and we will write this as omega n square. So I will rewrite this as s plus a by 2 square plus omega n square, and I will rewrite this further as I go on. But let me remind you of something which probably you have done in your circuit theory or network analysis courses. When you look at the RLC series circuit with a, say, a DC voltage and a switch, the problem of what happens, how the current builds up, how the voltage across the capacitor builds up, or the current decays rather, the voltage across the capacitor builds up when the switch is closed. This is a problem which is one of the basic problems in network analysis, and I hope you have solved that. Now that involves a similar situation. In fact, I told you a long time ago that one way of getting a differential equation is in network theory, that is in electrical engineering. The other way is in mechanical engineering by having a mass spring dashpot system. And remember, we talked about analogy between the two. So probably you have already looked at such a thing from that course. If so, you should look up that material. So, the denominator polynomial a square plus as plus b I am going to write as s plus a by 2 whole square plus omega n square. Now, I am going to do some further manipulation here, which will not be clear right now, but as we go on it will become clear. I am going to write this as s plus that a by 2 term I am going to write as delta omega n square plus omega n square. So, I have introduced omega n and delta, these two new things. So, what is this omega n? Omega n was defined from omega n square equal to b minus a square by 4. This was omega n square. So, the positive root of that gives you omega n. So, if I know b, if I know a, if the discriminant is negative, then this indeed will be positive, and therefore, square root of that will be a real number. I take the positive square root, think of that or call that omega n. So, that is my omega n. Then I have this a by 2. This a by 2 I can write as delta omega n, and therefore, I will write here a by 2 equal to delta omega n. I know omega n, I know a, so from that I can calculate delta. So, the quadratic will be now represented in terms of omega n and delta. I have used omega n earlier, if you remember, n for natural. So, in a sense it is called a natural frequency associated with that quadratic factor, omega n, n for natural. The delta, the letter delta is used because it should remind you of damping, and we will see how that damping arises. So, it is called the damping ratio or the damping coefficient. So, that is the damping ratio or the damping coefficient that one can calculate. Let me illustrate this for a very special numerical case and show that it is not really that difficult. It is of course possible to write down formulae. For example, here is a formula for omega n, there is a formula for delta, and then substitute and solve. But as I have been saying all the time, it is not enough to just remember formulae and substitute and get correct answers, because you must understand what is going on. So, let us see how this can be applied very simply for a very simple numerical case. So, let me take the polynomial s squared plus 2s plus 2. Now, of course, I know this polynomial earlier, I have thought about it earlier, therefore, I can go ahead with it. Let us check that the discriminant is indeed negative. So, what is delta? The coefficient of s is 2, so 2 square minus 4 times 2. So, that is delta is minus 4, that is less than 0. So, this is indeed a fit case for the complex roots situation. Now, instead of substituting and getting omega n and delta, I will complete the square as I showed you just now. Take s squared plus 2s, complete the square. So, I will get s plus 1 squared, that is s squared plus 2s plus 1, but I have 2 here, therefore, plus 1. It is as simple as that. S squared plus 2s, so this 2, from that I borrow 1 to complete the square, and the remaining part is 1. Now, what is omega n then? Omega n is 1. And what is delta? Well, this thing delta omega n, this is delta omega n, and therefore, delta omega n is also 1, therefore, delta equal to 1, right. I can do it with another numerical example. Let me show you. So, let us say s squared plus 4s plus what? Think of completing the square. So, I have s squared plus 4s plus 4, and therefore, let us say s squared plus 4s plus 5. If I complete the square, this will become s plus 2 whole square plus 1. Therefore, omega n is equal to 1, and my delta omega n in this case will be 2. Right now, do not worry about the fact that this delta may turn out to be greater than 1 or less than 1. We will see what exactly this delta is doing. But I am simply telling you that this delta you have perhaps encountered earlier when looking at the RLC series circuit. The resistance produces a damping in the circuit, and the capacitor voltage and the circuit current, if there is no resistance, then we can have a sustained oscillation, but if there is a resistance, then there is no sustained oscillation, and that is what is called damping. So, this delta is to remind you about that damping, that is all. So, this is the situation now. Therefore, when I look at the Laplace transform of omega s change delta omega s, that will be given by alpha by s into an expression in the numerator, and in the denominator I have s plus delta omega n square plus omega n square. This is what I have. Now, one can show the following. This I can split into two partial fractions. In other words, I keep the quadratic as it is. I do not factorize it into linear factors. If I do that, I get complex numbers. I have to do complex arithmetic. But I can keep the quadratic as it is, and I can split this into two partial fractions. one will be as before a1 divided by s, and that is obtained by exactly the same technique. Suppress the factor s and put s equal to 0. So that will be alpha g0 as before. The second term will have the denominator which is already there, s plus delta omega n square plus omega n square, right? And in the numerator I will write the expression as a2 times s plus delta omega n plus a3 into omega n square. This is one way of writing it. There are other ways in which one can write the expression. So I will break it up into two parts. One part has s plus delta omega n, the other part has omega n square appearing there. Now why am I doing this? Because there is a theorem of Laplace transformation, and I would like you to look up your book, textbook, either the mathematics textbook or the control textbook, to look up this theorem or result about the Laplace transformation. And that is as follows. If I have a function f of t, let us say, and its Laplace transform is denoted by capital F of s in keeping with our notation, if I multiply this function by an exponential function, if I multiply it by say e raised to minus at ft, remember this a may be positive or negative, so this multiplying factor may be decaying or growing, does not matter which one it is. I multiplied by an exponential, and you will see why I am writing minus a here. Then what will be the Laplace transform of this function? Let me call this function g of t. So the original function ft is now changed by multiplying by the factor e raised to minus at. The original function had Laplace transform f of s. The new function has Laplace transform g of s. What is the relation between g and f? The relation is a simple one, g of s equals f of s plus a. And so one easy way of remembering this result is multiply the function by e raised to minus at. This is an operation in the time domain. In the s domain, replace s by s plus a. That is, in the Laplace transform for f, whatever expression you have, replace s wherever it occurs by s plus a. You will get the Laplace transform of this new function g. This is a theorem from the Laplace transformation theory. Look it up from your textbooks. Make sure that you have understood the theorem correctly. You can apply it for a few examples to get some practice. It is this theorem that I have in mind when I have written the numerator expression in this peculiar way, because you can see that I have a s plus a kind of thing appearing here, s plus delta omega n appearing here, and both in the numerator and denominator. So I am going to use this theorem in a backward direction, as it were, to get something about the behavior of omega as a function of time.